In the last two videos, we have covered surface integrals of functions, such as scalar fields that are over surfaces. But now our surface is not given parametrically, but it's given in the form z equals, well, in this form here, 2x plus 2y plus z equals 4, which is, we can rewrite this in the form g of xy equals z. And once it's given in that form, there's a different way we can compute the surface integral, and that will be covered in this video. So if our integral is in the form, so if we have f of xy, that this is not changing. There's two ways. So in the previous videos, I'm gonna put this up here. In the previous videos, we've covered integral d and then f r u b and then times the magnitude of r sub u cross r sub v dA. But an equivalent way, if we have it in a different form, is d, and then what we can do here is we can take, let me take this. Okay, so we don't have this thing anymore, but instead of this thing, what we replace it with is the square root of the partial derivative of, now g is going to be equal to z. This is the form that we will have our surface in. So partial of g with respect to x, square it. Partial g with respect to y, square it, and then add 1, and then this is going to be dA. Here, guess what this is going to be? Well, it's going to just be f of x, y, not z, but g of xy. We don't have any z's. So, and I'll just write that up here. So g of xy equals z. So that's kind of three separate ways you can compute this based on the way the surface is defined. So if we have double integral s x z ds, s is the part of the plane 2x plus 2y, so I'll make that 2x plus 2y plus z equals 4. I'm just going to write this as z equals 4 minus 2x minus 2y. So that's g of xy equals 4 minus 2x minus 2y. So that's very good, because now we can write our function f of x, y, z, which is xz, into the form f of x, y, g of xy, which is equal to x times z, which is 4, minus 2x minus 2y. Or 4x minus 2x squared minus 2xy. That's what's going in here. Sorry, not there. In here. Next, we can find partial derivatives. Partial derivative with respect to x is negative 2. The partial derivative with respect to y is also negative 2. So, therefore, the square root of the partial derivative x squared, partial derivative with respect to y squared plus 1 is square root negative 2 squared plus negative 2 squared plus 1. Square root of 4 plus 4 plus 1, which is the square root of 9, which is 3. That's going in for all of this. Alright, let's set it up now then. So this is going to be double integral. Now, before we set it up, actually, the reason why I deleted it is because we need to define our region D. What's that going to be? Well, let's graph. So let's graph the surface x, y, z. Excuse the dog bark if you can hear it. Let's graph the plane. So the plane is 2x plus 2y plus z equals 4. If I set my x and my y equal to 0, z will be 4. That's the first point. If I set my y and my z to be equal to 0, x will be 2. If I set my my x and my z to be equal to 0, y will be 2. So here's the plane. And it's going to extend, obviously, but we can draw this and it will suffice. We want it in the first, we want this plane that lies in the first octant. What's the first octant? That's this octant here. This space. So I should draw it like this. This space that's on top. On the top. That's the first octant. Oh no, I can't revert this back. I have to erase it. And yeah, so that's the first octant. So that's going to be this portion here. And just to take that and draw it over in my xy plane. And again, D is going to be in terms of x and y. And so you need to essentially have it in terms of x and y, and you have to just set the integral up based on this region that's on the xy plane. Let me repeat that. You're setting up the integral and you have region D. In order to find this region D, it has to be in terms of x and y. We have to find whatever this is on the first octant, x and y. And set it up based on that region on the xy plane. So that's what's going to give us the bounds for x and y, is what based on the region that we see in the first in the xy plane on the first octant. Okay, let's draw it. This is going to be 2. This is also going to be 2. And so we have our line. Draw it. And then we have these right there. So the x can go from 0 to 2, so from here to here. But the y has to go from 0 to not just 2, because that would be the rectangular region, but to this, whatever this line is. Whatever that line is, we're going to set that up. It's going to be 0, 2, 2, 0. Those are the points. So to form our line, we can do 2 minus 0 over 0 minus 2, which is 2 over negative 2, which is negative 1. So the line is y equals negative x plus 2. And that's exactly what it's going to be, negative x plus 2, or 2 minus x. Here we have our bounds. We can set up our integral. Our integral is going to be, so x is going to go on the outer portion. Okay. And then we have 0 to 2 minus x. And then here we have f of xy, comma f of xy, comma g of xy, which is going to be 4x minus 2x squared minus 2xy times 3. dy dx. Let's compute. So simplifications, 12x minus 6 x squared minus 6xy. Let's break it up into this region, or this integral first. 0 to 2 minus x. This is 12xy minus 6x squared y minus 6xy squared over 2, which is just 3x y squared. The zeros will not bother me. They'll be nice, but the x, the 2 minus x will. So it's going to be 2 minus x minus 6x squared times 2 minus x minus 3x times 2 minus x squared. x minus 12x squared minus 12x squared plus 6x squared. Okay, that's good. 2 minus x squared is 2 minus x times 2 minus x, which is 4 minus 2x plus x squared. So it's 4 minus 4x plus x squared. Which gets you 2 minus 12x plus 12x squared minus 3x cubed. Making sure this is right. A lot of expansion. Minus 12x plus 12x squared minus 3x cubed. That's right. This will cancel with this. And let's see. We can do some other simplifications. 24x minus 12x is... Actually, let me go with this cubed first, the highest power. So negative 3x cubed. That's done. And then we have 24... negative 12x squared plus 6x squared is minus 6x squared. And then we have 24 minus 12, just plus 12x. And that's it. We take this now and we go here. So integral 0 to 2 let me see if I'm forgetting a constant or something. 3, this, and then this 3. I didn't bring it out, I put it in. Yeah, we didn't. Okay, that's good. Make this 2 plus 6x squared. Again, 0 doesn't bother me. It's negative 3/4 times 2 to the 4th minus 2 times 2 to the 4th plus 6 times 2 to the 2nd. Oh, 2 to the 3rd. 2 to the 3rd. This is 2 to the 3rd. And 3 to the 4th. 2 to the 3rd. What I did here is I just multiplied these and added the exponents in my head. Okay. So this is going to be 16 times, so I write this out, negative 3/4 times 16 minus 2 times 8 plus 6 times 4 minus 12 minus 16 plus 24. Some quick mental math. And minus 28 minus 28 minus 28 plus 24 is, drumroll, 4. That's the surface integral. These take time because of the setup at first, I think. Let me see. Yeah, they take time mainly because of the setup at first and then the integration. So like setting it up with like finding the partial derivatives, and then for at least here it's like quite obvious, and then finding the region to integrate over, and then setting it up, just finding these things. First of all, setting up the function, and then finding these things, and then finding the bounds, and then integrating. So it takes a while to do all of that, but it's worth it at the end if you get the right answer. So that's my work for this problem.